So we're in your chemistry book, section 3, chapter 9, Intermolecular Forces, Forces Between Molecules. And so these are just the important forces that we have, and they're between molecules, not holding the atoms together like the covalent and ionic forces holding them together, but those forces that are between each molecule that are holding the whole substance together. So this determines, intermolecular forces determine if something is going to be a gas, liquid, or solid at given temperatures and how they hold together. And inter means in between molecules. Whether it's dissolved in water, you can know if it's dissolved in water or solvents because of these intermolecular forces. And solids could not even exist as solids or liquid state without these forces. So we're talking about intermolecular forces that hold things together. Molecular weight and intermolecular forces affect boiling points of certain things. And when they're in a boil, then they'll know that the stronger forces, they're going to have higher boiling points. Now let's start talking about those forces. These are intermolecular forces. There's 3 different kinds. We're going on. We're going to start with the dipole. Don't let that confuse you. Dipole means 2, and these are polar bonds because they have basically have a negative side and a negative pole and a positive pole. So they're called dipole forces, and these are in between the different molecules. And here's a picture of them here. So you can see, like, here's this little half S8, this kind of little Greek number means partial. So here's a partial positive, partial negative, partial positive, partial negative, and they all have these, and so they're drawn, usually positives, of course, they're drawn away from positives, but they're towards negatives. So these are, in this molecule, they're being drawn in all these different ways because of dipole forces, and these forces will hold the substance together with the different molecules. Those are called dipole because they have they're polar, they have which is opposite ends, unequal sharing. They are not symmetrical because they have those 2 ends, and they basically also have their boiling points, will be a lot different. We'll talk about the boiling points in a little bit, though. In fact, in the next section up here. So actually, here we go. Since dipoles have only partial charges rather than full charges found in predominantly ionic compounds, dipole forces are not as strong as ionic. Remember, ionics, when they turn into ions and they put together, they give up an electron, and one's positive cation and one's an anion. So these are just partial. So they're a lot weaker than ionic forces. So now we have this picture. We can see how the boiling points of this. We have 3 different compounds here of similar molar mass, and they increase polarity in the molecule. And you can see how they do that. Generally, the more polar the molecule, the greater dipole force. So if it seems to be a more polar molecule, it have a higher force, and you can see the higher boiling points of those that basically have a more the dipole force is higher in those, so of these different compounds. So you can see that the boiling points, the more polar they are, the molecule, the greater dipole force and the higher boiling point. So that's the first one. The second kind of force is called the London force, and it's very weak. The London force, basically it was explained by Fritz London. That's who labeled it the force. It's a phenomenon that even the nonpolar, that means they don't have poles, they don't have positive, negative, even those kind of molecules seem to have a bit of a charge. Well, where did that charge come from? So he directed that regular molecules still had a charge, and that charge very weak because of the electron cloud would move around in the midst of atoms. And the larger the atom would be, the larger the molecular atom would be, the larger that London force would be. So let's talk about that. So even nonpolar molecules experience very weak attraction in interreacting, and the London forces affect all atoms and molecules. Every atom and molecule. So when it says, what are the forces? And you could pick dipole, London, or we're going to go over hydrogen. Every single molecule is going to have a London force. That's what Fritz London developed, right? And told, and it does. So all of nonpolar, even if it's nonpolar, it's going to still have, even though nonpolar atoms do not have a positive and negative pole, they will have a slight positive and negative force. Every atom does, he says. Okay, let's go on. London forces are the only type of intermolecular force that affects nonpolar molecules. They affect all molecules. And Fritz London lived in 1900 to 1954, so it wasn't that long ago that he found out what this London force was. And it comes with all molecules. Okay, here's a good picture of the London force. So the electrons are uniformly distributive with basically, as you see there, they're just uniform, so there's no poles in this one. But the upper atom becomes temporary a pole because all of a sudden, maybe all the electrons are coming up to this side, and so you have a temporary little tiny negative and a tiny positive. But this changes in a moment. And the lower atom becomes temporary dipole, and then at this point is attracted. So basically what it is, the electrons uniformly distributed, no attraction. Just for a moment in time, suddenly it becomes, because of the electron pool pulling over at the top, to the top or the bottom or side or wherever, you're going to have a slight positive and negative pole, but only for a moment. Those are the London, so it's a very weak force. For an instant, it will become the dipole, this momentary attraction between molecules, and then it will vanish back to the original momentary little, as the cloud moves around in there, a momentary little charge that doesn't lasts only for an instant, but it can be significant sometimes, especially if it's a very large. The larger the molecule and the larger the amount of electrons, then it's going to be larger London force. And it also, with the larger amount of force in the midst of all of that, if you have a lot of substance, so if you have a lot of substance, it's going to show up in your force if you have a lot of substance, because you know a trillion different atoms, and they all have a little bit of London force. So the London force on the whole is a weak intermolecular force resulting from instantaneous dipoles in the molecules. The polarizability is another word you have. What is polarizability? Let's go on here. Here we go. Right here. Property, the more easily electron cloud is distorted, a property known as polarizability, the greater the length of the London force. So if it's distorted very easily and it's a bigger molecule, it's going to have more London force, is all that means. So boiling points for similar compounds tend to increase with the molar mass. Why is that? Let's look at this picture here, the boiling points. So if you have here the boiling points, and these masses are the molecular masses of these are becoming more, so they're going to have more distortion, and they're going to have bigger molecules, so they're going to have more energy or more London forces. So you can see how the boiling points have gone up as the bigger molecules with London force. Boiling points and molar mass. As the molar mass goes up, the bigger the atoms, then their boiling points are higher because of the London force is higher in the bigger molecules. Okay. So let's go on to hydrogen bonds. Hydrogen bonds here. Hydrogen bond is a very, very strong force. Hydrogen bonds are covalent bonds that are strong, they have a strong electro negative atom. So they, especially with oxygen, but with also nitrogen and fluoride. Three different ones here that basically have a very, very high intermolecular force. And that is between hydrogen and nitrogen, hydrogen and oxygen, and hydrogen and fluorine. Those three very, very high hydrogen force. So hydrogen are very strong with oxygen, nitrogen, and fluorine especially. And because they have that very strong electro negative as atoms drawing them in. Electrons are pulled very heavily away, leaving hydrogen bare in their nucleus, very strong positive on the nucleus. That's why they say the hydrogen bond will have a really, really strong polar nucleus for hydrogen, because hydrogen basically, that electron is just pulled away really quickly. So, or strongly, I should say. So these here have very strong dipoles, which are pulling on them, and the hydrogen bonds usually have very strong intermolecular force between the molecules and containing hydrogen bonds to highly electronegative atoms, like I said before. Hydrogen bonds, a lot of are just look like dashes. Whenever you have a little dash, that means a hydrogen bond right there. It's not like hydrogen bomb, I'm saying, but hydrogen bond, okay? Just know hydrogen is the strongest. Here's some pictures of some pretty strong hydrogen forces between them. Now, it's not the forces that are holding these together with the hydrogen and the oxygen here, or the hydrogen and the nitrogen here, but it's in between, very strong in between bonds between the hydrogens and each atom. So they have a very strong forces in between, the intermolecular forces in between these, as you can see. And here shows the strength of all these. There's lots of intermolecular forces holding these hydrogen, and pulling these hydrogen in certain ways because of the high negative forces there, electronegative atoms. So here we go. So let's look here. Oh, this is pretty interesting. The effects of hydrogen bonding on the boiling point. So here are hydrogen. This is carbon. This is with nitrogen. This is with fluorine and oxygen. These are they combine very easily with hydrogen. So you see the forces there when they combine. You'll see as they combine, group 16 and they have the groups here, but basically, so you'll see the high boiling points. You see, here they are here in the midst, and they combine and they have a very high boiling point. And so you can see when they combined with hydrogen, they're going to have a much greater force called the hydrogen force, right? Hydrogen bond force. So it's a very important force in nature, all this hydrogen. So let's go one more thing here, and then I'll just kind of go over some of the questions. But let's go over this table here. This will tell us. So you're going to have probably some of these on your test questions. So you have London force and dipole forces and hydrogen bonds. So London forces are found in all molecules. Dipole are only in polar molecules. And hydrogen are only in hydrogen molecules. So that's the difference there. London forces are very weak. And dipole are pretty strong because they're polar, right? But hydrogen are very, very strong, the strongest of the covalent bonds. 5 to 10% of the strength of the covalent bond. So it's a very strong intermolecular force. And then the London forces only are just a momentary attraction, and then they go back to normal, just an instant. And dipole are constant they're constantly going between weak partial charges going throughout the whole time. They're constantly, and hydrogen are constantly attraction, but they're very strong partial. They're strong charges, stronger than dipole. So that's the difference. Here's the weakest to the strongest, right? Okay. Let's look at the questions really quick. It says, how are intermolecular forces different from chemical bonds? Well, basically the inter means in between molecules, and the bonds are in molecules. So basically the covalent are holding the bonds together, like in basically holding the bonds of different atoms together into a certain substance. And the intermolecular are those in between, in between the molecules. Hope that can explain that right. Explain the dipole-dipole force. The dipole-dipole force are charges are basically dipole-dipole are where you have different poles, two different poles in the midst of them, and they're attracting. They're polar molecules that are attracting, and their charges. They're slightly charged. They're going to be a partial charge of negative and partial charge of positive in between molecules that kind of hold them together in the midst. What causes London forces? London forces result from an instant cloud change of electrons. And this instant cloud change gives us a very, very weak, but still significant in a large force of holding together, a force in between positive and negative because of that. London forces are in every single molecule. Explain the difference between hydrogen bonds and dipole-dipole. Hydrogen bonds involved the hydrogen have to be the hydrogen atom, right? And they have a very strong, because when you take hold of that hydrogen, you're going to leave the hydrogen bare. So they have a very strong positive. And so this very strong positive with a very strong negative bond there is going to cause intermolecular forces to be very strong. So basically you have to have a hydrogen with a hydrogen bond. So tell which of the intermolecular forces would exist between molecules of the following substance. Okay, so if you had polar here, which one was polar all the time? Which one is always polar? Dipole-dipole is polar, right? But it also, every single molecule has London, so London would be for that one too. And also you notice it has a hydrogen in there, so it's going to be all three. It also will be hydrogen, so it'd be all three would be in this one. H2O, which is water, would be hydrogen, of course, and it also would be dipole-dipole because water is polar, so it's going to be dipole-dipole, and it would be hydrogen, and it'd be London. All three forces there in that one too. D is a non-polar one, so only non-polar ones are London. So London is only this one. The other ones are not there. HCl. HCl being hydrogen, so we know it's hydrogen, and we also know it is not only hydrogen, but we know it's going to be London. So hydrogen and London, that will be. And which one is that? Hydrogen. And onto this one. Here's polar. This one's a polar one, so we know that polar is going to be, first of all, it's going to be, if it's polar, it's going to be dipole-dipole, and it also is going to be London because they're all London. And is it going to be hydrogen? No hydrogen, so it's only going to be these two. Okay, CO2 is non-polar, so since it's non-polar, it can be London, and that's it. Any non-polar can only be London, and that's the only one because it's non-polar. The other two, this one has to, basically the London forces can be all molecules, but these two, this one has to be polar, and so does the hydrogen, it has to be polar. And so here's another hydrogen, and of course this is a polar one. polar one. So this is going to be hydrogen. It's going to be the hydrogen because it has hydrogen here. It also is going to be polar. So it's going to be dipole, right? Because it's polar, and it's going to be London. So this one will be all three. 1, 2, 3. So that's how we go, and that's the end of that section. And let's see, we'll go on to the last section, which is pretty short, and then we'll take your test.